Once upon a time, in a country far, far away, the queen of the country and of all Möbius strips called for her royal philosopher.
Philosopher, I ask you to carry out the following order. Get me the philosopher's stone, or alternatively, find out how one could produce arbitrary amounts of gold with it.
But my queen, I haven't studied anything useful. How could I fulfill this order?
This is not my concern. I'll see you again tomorrow. Should you not accomplish the task, I will take your head off.
After a long and wakeful night, the philosopher was called to the queen again.
Tell me what you have to report.
Well, it was not easy and I needed to follow lots of obscure references. But finally, I actually found out how to use the philosopher's stone to produce arbitrary amounts of gold. But only I can conduct this procedure, Your Royal Highness.
All right, so be it.
And so years passed by, during which the philosopher imagined himself to be safe. The queen searched for the stone on her own, but as long as she hadn't found it, the philosopher didn't need to worry. Yet one day, the impossible happened. The queen has found the stone and promptly called for her philosopher.
Philosopher, look, I have found the philosopher's stone. Now live up to your promise.
Oh, thank you. Philosopher's stone. Many years ago, you asked me to either acquire the philosopher's stone or find out how to produce arbitrary amounts of gold using it. Now it is my pleasure to present to you the philosopher's stone.
Thank you very much for joining in this play. So if you're wondering what this play has to do with the talk, then stay tuned. It will get explained. And thank you very much for setting up this meeting, dear lovely local and also other organizers. I have been looking forward to this for months now, especially because so for lots of people, I've been following your work for like a long time, but I have never interacted with you, not least because I was not able to attend the last couple of TYPES meetings. So I'm really, really happy to be here. And this is an invitation to follow along. I will present a certain perspective which has grown in my mind over the last couple of years, a certain kind of language, certain kind of tool. I hope that it's useful to some of you, and I hope that in the very least it's of interest to you. Feel free to interrupt me mid-sentence. Don't wait till the end for your questions. We have these nice microphones, so the acoustics will work out. And in case you've seen a similar talk of mine before, I chose to present the new advanced results only in the end, and first make sure that everyone is on the same page. So there will be some repetition. And to keep the talk grounded, let me do a running example in combinatorics, not in advanced algebraic geometry, just in combinatorics, which should be easier to make sense of. Let X be a quasi-order. By that, I mean a set or type with a relation on it, which is reflexive and transitive. Then we call a sequence to be good if and only if some earlier term in the sequence is at most some later term in the sequence. And the quasi-order itself is called well if and only if every infinite sequence is good. And thereby we set up the theory of well quasi-orders, which is quite important in some areas of computer science and, let's say, proof theory. We can use these, for instance, to verify termination of algorithms. Here's an example for a well quasi-order, namely the type of natural numbers with the usual ordering. That will be a well quasi-order. There are several proofs of this fact, constructive ones, very quantitative ones, also classical ones. Just for fun, let me present a classical proof. So let alpha be a function from n to n, an infinite sequence of natural numbers. Then appealing to the transfinite, we know that this function attains a minimum somewhere, alpha of I. And then, of course, alpha of I is less than or equal to all the other terms in the sequence. In particular, it's less than or equal to alpha of I plus 1. So we succeeded in verifying that every sequence of the natural numbers is good. Okay. So that's an important example. And here are three important stability results telling us that the notion of well quasi-orders is closed under certain constructions. Firstly, given two well quasi-orders x and y, we can form their Cartesian product with a pointwise ordering, and that again will be a well quasi-order. But we can also put certain orderings on the types of finite lists of elements of x and certain kinds of trees of elements of x. And then also observe that these resulting orderings are again well quasi-orderings. With this tree result, we can set up this extremely fast-growing tree function where tree of three has gained this cult following in the internet. If you belong to the members of that cult, get to me after the talk. I have a tiny present for you to take around in your pocket. Okay, so that's the basic of the quasi-orders. There's one issue, namely, well, we need the lobes through the middle and perhaps also the axiom of dependent choice in order to prove these key stability results. We should do better. And several members of this audience have done better and have devised a constructive alternative definition. So let's rename the original definition to be well infinity. And then there is a new constructive definition called well index IND. And it's given by this definition. In classical mathematics, where we have the principle of bar induction available, this new definition will be equivalent to the original one. But in constructive mathematics, the new definition has better properties. In particular, we can verify all the key stability results constructively. So that is nice. That has already been done. That has already been explored over the last, I think, 30 years by several people. Personally, I learned this definition by Sylvia Steyler, but it's due to, I don't even know. It was worked on by so many people that I'm unsure who discovered this inductive rephrasing first. However, as logicians perhaps, we are not yet done. So yes, those people have succeeded in giving a constructive account of the theory of well quasi-orders using this definition. However, their proofs are quite alien if you compare them to the original classical mathematics proof. Alien in an alluring and very interesting and intriguing way. So I encourage you to all check out their proofs. However, they also don't look at all like the original classical logic proofs. They are really quite distant. Mm-hmm. In the definition of what good means, namely a finite sequence is called good if in that finite list an earlier term is at most some later term. Yes?
Do you not explain how to understand the definition of finite list?
Yes, I don't. So this definition here only refers to finite lists, and that's important. And then I just say a quasi-order is called well inductively if and only if this inductively defined predicate holds. And no infinite sequences appear in the definition any longer. And that's the point of that definition, to avoid the infinite sequences. The challenge is to do the following. Is there a procedure, some kind of technique for interpreting the original classical logic proofs of those key stability results as blueprints for constructive proofs? So the task is not to devise constructive proofs on our own, but instead to have them extracted from the classical logic proofs. And in many cases, this vision does work. You could call it a version of Hilbert's program. And it works, for instance, beautifully for this classical logic proof here. How do we constructivize that? So as an algorithm, as a Turing machine, I will not be able to find a minimum. For that, I would need to inspect all the terms in the infinite sequence, which I cannot do. However, I can cheat a little bit and just exclaim that alpha of 0 surely needs to be the minimum. And then the next step in the proof will ask of the minimum to provide witness that indeed alpha of 0 is at most alpha of 1. And perhaps that happens to be true. Then the cheating worked out beautifully. It might also be incorrect, but then I just change my mind and now I re-exclaim, surely the minimum of the sequence is alpha of 1. And then we have the same story on again. The next step in the proof will then inquire a witness that alpha of 1 is at most alpha of 2. This might work, then everything works out nicely. Else, I just re-exclaim, change my mind again, and say, surely the minimum is alpha of 2. And after a finite amount of steps, this process will terminate. So getting rid of double negation, getting rid of the loss-rule middle is not that hard in practice if you're used to working in this business. When you first encounter constructive mathematics, you might think that it's like a totally different thing. And but in fact, at the expense of introducing a couple of double negations, we can get rid of the usage of the loss-rule middle in many cases. If you are only dealing with first-order situations, and here we are dealing with functions, and there it's a little bit different. And indeed, the usual double negation translation, which we use to constructivize proofs like the upper left, will not work for those results. We first need to find this totally different alternative definition. To appreciate the work which others have done in setting up this definition, let me just sketch two of the proofs in the theory of well quasi-orders. The details are not important at all. Just the general outline is important, like which ingredients, which axioms are used in those proofs. So, for instance, at the upper left, we have this result that given as an infinite sequence, we will always be able to find an infinitely long increasing subsequence. The way we do that is as follows. We consider that type I of those terms which are missing a right partner. And if that type I was in bijection with the natural numbers, we could extract an infinite subsequence, which is nowhere good. That's a contradiction to wellness. So by the laws of the middle, the type I is finite. And then we can just pick some index larger than all the elements in I and use this as a starting point for an infinite sequence. We will always be able to find a next term because all the sad terms which don't have a partner are only in the beginning of the natural numbers and not beyond I0. Okay, so that's a classical logic proof. It's outrageous from a constructive point of view. This lemma, the statement of the lemma would imply the infinitary pigeonhole principle, for instance. So it's definitely a constructive taboo. Okay, so we have a transfinite tool, but it can be used to obtain concrete consequences, not infinitary consequences, but very finitary ones. For instance, this result called Dixon's lemma, but the product is again well. If we analyze the situation in more detail, then we will find out the following. The classical logic proof on the left uses the law of the middle. Usually that's no problem. We can just get rid of applications to the law of the middle by doing this iterated cheating like with the natural numbers and like performed in the play. However, here it doesn't quite work. And the reason is that by the law of the middle, we are building up in the first part of the proof, in the first step, a certain subsequence, and then are obtaining the contradiction by referring to wellness. And we kind of hope that the definition of wellness also refers to that extracted subsequence. However, that subsequence was constructed using the law of the middle. So it's not actually a function from n to x. Instead, it's a partially defined function from n to x, where every function value does not exist. But it's not actually a function. It's not a member of the type of functions from n to x. And hence, the wellness we are given does not refer to this kind of sequence. And hence, we cannot carry out the first proof step. And that is why a totally different definition is needed, namely the definition on the previous page. And now I'd like to present a possible origin story for that definition. It's surely not the historically correct origin story. Instead, it's a modal logic, topological, toposophic origin story, and perhaps you will like it. Any questions, comments right now? Okay. Then let me tell you about forcing. This technique in set theory pioneered by Cohn in the 60s, for which he was awarded the Fields Medal, which, by the way, is the only time in history that a Fields Medal was awarded for a work in logic, in foundations, stuff like that. If you always had like looking up forcing on your to-do list, but were always a little bit scared of the layers of set theory, perhaps this will be your day, because I will present, in my mind, very simple type theoretic approach to forcing. Recall from ordinary mathematics that often we enlarge given mathematical structures so that they better serve the purpose, so that they are better in certain senses. For instance, we pass from the rationals to the reals to embrace the irrational numbers, or we pass from the reals to the complex numbers to have a square root of -1, or we pass from the complex numbers to the polynomial ring over them in order to have a generic number, which can later be instantiated by any concrete number whatsoever. Okay. You will find no issue with these three examples, but recall, just let's say 300 years ago, those things were highly problematic. Not least, the square root of -1 is called the imaginary number. And I think a big part of why it's nowadays not a big issue, why we routinely work with the reals and the complex numbers and polynomials and so on, is because we have understood in which sense they can be regarded as a convenient fiction. You see, every claim about the real numbers will in the end just be a claim about rational approximations to those numbers. It's sure convenient to have the number pi as a reified real number, but if I was like forced to do without the reals, I would be able to do that by instead working with the rational approximations. Similarly, with the complex numbers, every complex number can be regarded as a pair of two reals. So every assertion about the complex numbers can be reinterpreted as a pair, as an assertion about pairs of real numbers. So nothing mysterious about that. And then Cohn in the 60s went one step further. Instead of enlarging a given structure within mathematics, he devised a technique called forcing for enlarging the mathematical universe itself. By mathematical universe, I don't mean U0, the first universe in many flavors of Martin-Liv type theory. I mean all of our mathematical context, yeah, containing perhaps lots of type theoretic universes, depending on the meta theory we are working. So what can you do with forcing? For instance, you can force the existence of a new function from n to x, a new function which was not there before. Or you can force the existence of a particular kind of new functions from n to x, namely of a surjection from n to x, thereby rendering x countable in the enlarged universe. This is called Levy collapse, and I was extremely shocked when I first learned that, because I thought that countability of a set or type is just something inherent to that type, sometimes simply contain too many values for them to be countable. They are then uncountable. But I was mistaken. By passing to a larger universe, we can find a surjection from n to any specified type in the base universe. This, in that process, we neither add new natural numbers, nor do we remove elements from x. Instead, we invent a new function from n to x. And if you're into commutative algebra, then the third example is for you. You might know that prime ideals and maximal ideals are quite useful in commutative algebra. You might also know that in general, we need non-constructive principles to concoct them. Zorn's lemma, for instance, for maximal ideals and the Boolean prime ideal theorem for prime ideals. So we don't have these ideals available in constructive mathematics. However, we do have them available in constructive mathematics if we are willing to enlarge our universe. Okay. And then a central observation is the following. A quasi-order is well in the inductive sense if and only if the generic sequence is good. In this way, we can reduce the notion of inductively well, which is the good notion in constructive mathematics, to the naive point-based notion, which is just referring to infinite sequences. It's just that no sequence in the base universe does the job. Instead, we need to pass to a forcing extension in which we have the generic infinite sequence. And if that particular sequence turns out to be good in the universe it's living in, then this means this is equivalent to the original type in the original quasi-order in the original universe, in the base universe, to be well in the inductive sense. And that is the key for transferring the classical logic proofs, which were about the classical definition of wellness, to the constructive world. Here's a similar example. A relation is well-founded if and only if, for the generic decreasing sequence, we have bottom. Recall, if I look up on Wikipedia the definition of a well-founded relation, I will not find the definition which many of us cherish, namely this inductive ACC accessibility predicate. Instead, we will read that a relation is well-founded if and only if there are no infinite decreasing chains, decreasing sequences. From a constructive point of view, this Wikipedia definition is not of much use. Yes, it is satisfied by the relations we think to be well-founded, but it's a much too weak requirement. We can recover this naive idea by saying that the generic descending chain should validate bottom. And then a final thing, again, for the commutative algebra lovers among you, you might know Krull's Hauptsatz, 1929 Hauptsatz, which states that a ring element is nilpotent if it's contained in all prime ideals. Very useful criterion in commutative algebra. Also, unfortunately, not available in constructive mathematics. We need the Boolean prime ideal theorem again for that. However, if we rephrase that slightly, then it becomes, it is constructively available. Namely, a ring element is nilpotent if and only if it's contained in the generic prime ideal. So classically, we say all the prime ideals in the base universe, and now I say the generic prime ideal in a suitable forcing extension where it exists. On slide 5, I will show you how to actually do these kinds of considerations with the generic sequence and so on in practice. I will show you a little bit of Agda code. It's just that before I want to show 2 more fun facts and a couple of mottos extracted from these ideas. Go ahead. You're welcome.
Somehow you can use this generic descending chain idea to synthesize this ACT idea.
Yes, indeed. So let me repeat. It is true that the following works. From a witness that the generic descending chain validates bottom, we can obtain a witness of ACC X for all X in the type. Yes. By doing mostly nothing. So these central observations actually have quite simple proofs. So I would say if you are immersed in all the definitions, then it's just triviality. It's not like Agda's Ctrl+C, Ctrl+A automatic mode will find the proofs, but it's almost that. So the point of those was not proving these. Instead, it was observing these for the first time.
One meta-level question, the setting icons at the end of the config, that means that continues to.
You mean this icon?
Yes.
This icon means that in a week, you can click on that icon, and then you will be transported to Acta code, where you can read up all the details about these claims.
So then the way to go, basically, always formulate constructive.
Yes, yeah. My meta theory is constructive English, not classical English. And if I do need classical principles, I will always explicitly say so. Yeah. This third observation is, I think, due to Thierry Coquon, or perhaps other members of this dynamic algebra crew. The second observation here is not due to Simon Henry, but due to Sean Henry. And the first observation is, as far as I know, due to me. And all of those are not hard to prove. It's just hard to observe them. Just so you see that there's like actual content to those notions, let me share two surprises. Namely, you can also enlarge the universe in order to force the existence of a generic ring. You use the ring axioms for setting this up. And then amazingly, it will turn out that generic ring is a field, something which you would not have expected just from the general theory. Also, I like the following fun fact about the generic surjection from N to R. I'm already amazed that this surjection exists, yeah, because the real numbers are known to be uncountable, at least in classical mathematics. And I could put 2 to the n here, which is always uncountable in all flavors of mathematics, including constructive mathematics I know of. And an example would still work. But we have an even more specific fun fact, namely this, up to double negation, the numbers pi and e are adjacent in the generic surjection. And the same thing would work for any other 2 numbers, and also for any other finite list of real numbers. Who would have thought that? I mean, there's nothing in the idea of a surjection that this should hold, but it does.
That means that I and any other.
Yes, yeah, for any numbers you specify, for any 2 numbers or 3, 5, 4 numbers you specify, you will find one n such that the next couple function values are exactly the numbers you want. Yeah.
Again, neatly fun. Neatly fun.
Yes, up to double negation. Up to double negation. So it's impossible for there to be no such number n. Yes. And all of this claim does not play out in the base universe, where most likely we don't have a surjection from N to R. It plays out in an enlarged universe, in a forcing extension, in a Grothendieck topos, in which we do have the surjection.
Probability theory, because if you assume this, totally clear that the probability 1,
yeah.
If you assume, yeah, they have infinity of pi,
yeah.
Therefore also the next one, there must be probability 1.
Okay.
It's randomly distributed.
I see. Interesting connection. I will need to think about that. The actual proof is not related to probability at all. It's a like 3 or 4 line Acta proof, but nice idea. Okay. Let me do this slide and then an explanation how this forcing works. By topos, I mean Grothendieck topos. And by Grothendieck topos, I mean forcing extensions. For me, these are the same notion. So I introduced 3 modal operators in our language, namely everywhere, somewhere, and proximally, which is like a better version of somewhere. There's a thing called the trivial topos, the trivial forcing extension. In the trivial topos, any statement whatsoever is true, including 2 + 2 = 5. I need to exclude that topos from my definition of somewhere. I do that in a constructively sensible way. And for that, I turn to the notion of a positive topos. You don't need to be experts in topos theory to appreciate the rest of this talk. Don't worry, just an explanation of what roughly speaking positive means.
Yeah.
Is there a partial order on topoi? Yeah. Even better, there are morphisms between toposes, so they form a category. And yes, indeed, this category will have an initial object and a terminal object. Yeah.
Do you need classical logic in the meta theory?
No.
No.
No, 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 no. Yeah. Yeah, it depends, perhaps. Perhaps
unique choice.
Unique choice, yes, yeah. I must confess, I have a blind spot for applications of unique choice. I was not trained, or I did not train myself in seeing where unique choice is required. Yes, yeah. All of what I'm saying here works in a constructive meta theory, but more precisely, I should say, at the moment, it's mostly in extensional constructive type theory. Where we have function extensionality and where we have unique choice. Let me get back to. Well, if you talk to some of the people here, they will. Okay, I will be happy to listen to the discussion you will have with other members of this community. So here's a rephrasing again of inductively well, namely a type or a quasi-order is inductively well if and only if everywhere it's well in the classical sense, in the infinite sequence sense. That's mostly just a little addition to the central observation from the slide before, because it turns out that if the generic sequence is good, then all the infinite sequences in all the toposes are good. Then we have two results for passing between the base and the forcing extension, which is very nice because it allows you to, in the end, prove something in the base universe and just use the toposes, the forcing extension, as auxiliary tools. And then we have this statement that countability is a button in the sense that you can press it, but once it's pressed, you cannot unpress it. Namely, for every inhabited type, proximally, that type will become countable and it will remain countable in any further extensions. And then the law of Slough middle is a switch. Everywhere, we can switch it on and we can also switch it off if we want. Those model operators were first studied by Joel David Hempkins and his collaborators in set theory. And he was mostly interested in those operators in order to settle questions regarding the status of certain set theoretical principles, like the continuum hypothesis. It's very intriguing work. I encourage you to check that out. And I'm using the same idea, but for totally different purposes. I don't want to explore the range of set theoretic possibility. Instead, I want to get constructive proofs of results in classical mathematics. That is my goal. And the idea to study the topos theoretic multiverse in this modal sense is joint work with Alexander Oldenziel. In fact, it was his idea. Just so that credits are where they are due. And now let me explain how to actually work with those forcing extension Grothendieck toposes in practice. That's a 4-step procedure. And it's related to how you work with real numbers. If you are by law required to not explicitly use them, namely then you work with the finite approximations, with the rational approximations. So, for instance, for working with the generic function from n to x, we set up a type of finite approximations, namely the type of finite lists. I picture a finite list to be an approximation to a function from n to x, namely a function which has as values the values in the list, And when the list is done, all the other values are undefined. That way I can picture a finite list as a partial function from n to x, as an approximation to some kind of generic function. I will not actually have in Agda or wherever the generic function because it transcends the base universe. But I can kind of pretend that I have it because I have all those finite approximations at my disposal. I just need to reinterpret in a mechanical fashion every assertion about the generic function as assertions about its approximations. And the way how to do that is to look up the Kripke real semantics. They will tell you how to do this mechanic translation, this mechanic reinterpretation. Here's just one example. We might wonder whether f0 of n equals x. This is not an actual proposition. Instead, it's a stage-dependent proposition, depending on the current approximation. And I have this idea that over time, the current approximation will grow to a better approximation. And well, so it's from the point of view of the base, a function from L to prop, namely the function which takes a finite approximation as input, sigma, and then returns the type of witnesses that at the position n in that list we have x. And now a crucial inductive definition, very similar to the definition of that G from the first slide. We need to have a mechanism for evolving approximations to better ones. And we need to make use of this mechanism in front of all the hairy connectives in constructive mathematics, so in front of disjunction, existential quantification, and bottom. In front of all the positive witness-bearing connectors. So nabla p sigma expresses that no matter how sigma will evolve over time to a better approximation, tau, eventually p tau will hold. And it expresses that in a direct inductive way, using two constructors. Namely, if p holds for sigma, then indeed, including after evolving, this will hold. And the second is here, we may conclude that eventually p will hold if we know, if we are given that eventually would hold for any way how it could grow by one element on the right. That's the definition. And then to express that f0 is defined on input n, we would express that as follows. No matter how the empty list will evolve over time, eventually this will hold. And then indeed, that list will contain an nth element. Okay, that's the idea. Yeah.
Here, say that the notion of extension here and it would be part of point one. Like the notion of like the like that's not also the notion of extension.
Yes, indeed. Yeah. Officially, I should set up a so-called forcing notion, which for me is a Grothendieck site. Yeah? And this comprises a category of approximations together with a covering system telling me how to evolve approximations. And yeah, in the end, this nabla is a kind of monad. And so what we are doing when we are working with a forcing extension, we are doing ordinary programming, but in a monadic variant, monadic style programming for this particular monad. So our programs will now have side effects. For instance, if we work with a generic surjection from n to x, we will have the following side effect. In the beginning, we start with the empty list, right? Okay, and this might be sufficient for a long part of the of our program, of our proof. And then at some point, the proof will require a particular element to be in the range of the generic function. And at this point, we will have the side effect of enlarging the given approximation to include this additional element. And then the proof runs its course, and then it might happen again that it requires a certain element to be in the range, and then we enlarge the list again, and so on. It's just programming with side effects in the end. So I like this duality. In the one hand, it's like philosophically charged, yeah, alternative universes, enlarged universes, and so on. Quite amazing ideas. And in the end, it's just program with side effects. Something very basic, very down to earth. Let me also remark that this here is very much related to the definition of dialogue trees. For those of you who have been studying dialogue continuity and so on. It's just that you, namely the special case where P is constant in its first argument, then you obtain the usual dialogue tree definition.
Here you're in prop.
Yes, just ignore prop, say type instead, and then what I said just said is correct. Okay, and the amazing thing is that this is not some arbitrary translation, some child's play. Instead, a constructive reasoning is sound with respect to this translation. So it really feels like we are working in a universe where constructive reasoning is available, even though in the end, we are never leaving the base universe. We cannot leave the base universe. In the end, we are just dealing with this nabla moment. Let me make a comment regarding a formal implementation of all of that. So in the extensional setting, everything what I said can be made absolutely formal, absolutely precise. I have written ACTA code for that. And it's not my invention at all. Perhaps I was the one typing it up in ACTA, but it's so-called the cryptographic semantics and topos theory. No issues about that. But perhaps you want to go beyond extensional type theory and also have intentional versions of that. And then it's a little bit harder. Already the definition of a pre-sheaf, what you need for this to work, has its issues in intentional type theory. There was a breakthrough, I think, by this paper, Russian Constructivism in a Pre-physicist Theory, building up on several precursor works. But I'm not familiar with any new breakthrough beyond that. Please correct me if there is one. So we have certain restrictions. We need this. We do have this compilation procedure, but only to a version of CIC with a certain kind of strictness built into it. If we understand pre-sheaves, then sheaves are not the issue. That works nicely in an intentional setting. Have a look at these references. And before concluding with a couple of applications, let me just remark that we can use this nabla exactly with the ACTA definition I just presented, even if we don't have all the required formal backing. We can still just try to use it in ACTA. After all, ACTA will check whether I'm doing mistakes, right? So I really want the formal backing, but I don't, strictly speaking, need it. Mm-hmm.
So what are the exact postulates that you use in your ACTA code?
I'm not using any postulates.
Nothing on function extension?
No, nothing. Yeah. For the results I want to have, I don't need any.
And you don't use strict prop?
No, I don't use strict prop.
What do you mean with independent type?
Yes, Martin-Löf type theory with some flavor of Martin-Löf type theory with your favorite extensions. We then have coherence problems. Yeah. Yeah. If you're willing to restrict to H sets, then everything will be fine. Yes, for many purposes. But yes, I agree. I'm happy that you don't regard this as a huge restriction. Let me conclude the talk with this slide. You see here an example application of this outrageous lemma from the beginning, telling us that if every increasing sequence has a prefix validating B, then every sequence has a prefix validating B. And here you have a constructive reimagination. This expresses that eventually, no matter how the empty list evolves to a better approximation, B will hold for that. And this here expresses the same, but restricted to increasing finite sequences. So no matter how the empty list evolves to an increasing finite sequence, we will have B. Okay, and the point is, the proof of this is almost the same as the classical proof. Just that it's a little bit sprinkled by these modal words, somewhere the law student middle holds and so on. But other than that, we can just copy the original proof. And I implemented that in Acta already, I think, 1 year ago. So I had this algorithm available. In the end, it's an algorithm which we can run. But I did not understand this algorithm for quite some time. And only like a couple weeks ago, I was able to make sense of what this algorithm is doing. And I think that's just amazing, yeah, that nowadays, thanks to this approach using toposes, forcing, and so on, we can devise algorithms which we do have, which are checked by Acta and everything, but also we don't precisely know how they work. If you're interested in a live demo, ask me about that. And now let's stop. Thank you very much for your attention.